Okay, good afternoon everybody. Let's get started. So welcome to 6004. Today we're going to shift gears and start learning about operating systems, which are one of the major topics in 004. And so, you know, these operating systems is a big topic, so this will be an introduction. And we will focus on the interaction between hardware and software. So this is a topic where it is very important to understand what happens on both sides of the fence. This is also the part of 004 that is essentially the prerequisite to 6033. So if you take 6033, you'll see these concepts as an introduction of a more thorough discussion that you'll see in operating systems there. Okay, so broadly speaking, in 6004 so far, we've built machines, we've built processors that run a single program at a time, right? So there's some hardware. We've designed, this processor over here. We've looked at the memory hierarchy, and then, as you know, systems have all sorts of I/O devices, hard drives, network cards, displays, keyboards, mice, other peripherals, and so, we haven't talked a lot about those, but we will do that in a couple of lectures. But the key idea here is that as we've seen the system so far, this program that's running directly on top of the hardware has complete access to all the hardware resources, right? It's directly accessing the processor, it's directly accessing memory, and so on. And so remember that the interface that this program is coded against is what we call the instruction set architecture, or ISA, right? So that, we've seen RISC-V. There are many others. There's x86, ARM, and so on. And so, we're basically directly coding our programs against the hardware-software interface. Now, some systems actually work like this. So if you, for example, are looking at what we call embedded systems, right, where basically these are systems that do a single thing. So, for example, the elevator controller for the startup building, right? It's only controlling the elevators, and so having a single program running the whole system is a reasonable architecture. But most computer systems actually do not work like this, right? And so you already know this because in your laptops you're running multiple programs at the same time, right? And when you write programs, you're not directly accessing the hardware. There's a little bit more abstraction going on. And so what happens is, most computer systems are running with what we call an operating system, right? So instead of there being a single program in the machine, there are multiple executing programs, right on top over here, that share the machine, right? And each executing program does not have direct access to hardware. So instead, there is an operating system in the middle that's interposing between these programs, between these executing programs, and the hardware. And so this gives rise to two different interfaces. So the operating system is still going against the ISA, right? The operating system is talking to hardware, or at least it believes it's talking to hardware, as we will see later. But it is the only thing in the system that has unrestricted access to the hardware. These running programs above are coded against a different interface, which is what we call the Application Binary Interface, or ABI. Okay, so now you have two interfaces, and this gives rise to a number of system-level issues. Okay, so before we dive into what operating systems do and why they do it, let me shift a little, change the nomenclature a little bit, because we need to be precise, and because when we talk about operating systems, we don't really talk about programs. We actually talk about processes. And so here you see two changes, right? The first one is that here you can see that instead of program, right, I've changed the word to process, and here instead of operating system, I'm saying OS kernel. Okay, so first of all, the difference between a program and a process is a program is just the code. It's a collection of instructions. And a process is a program that is being executed. So it's the code plus some other state, right? It registers, what values does it have in registers, what values does it have in memory, what memory does it have allocated, does it have any other resources, does it have any open files, is it talking to some other process over the network. So that's the key difference, right? A process is just a running program. And then the operating system kernel is just another process, but it is a process that has special privileges. And we call it the kernel rather than the operating system because generally when we talk about operating systems, you talk about things like Windows or Linux or Mac OS. That includes a lot of other programs that, things like a text editor or a window manager that are not this thing that's interposing in the middle. They're just normal programs. And so we distinguish between the operating system, which is this whole suite of programs, and the kernel, which is this special with this process with special privileges that is talking directly to hardware. Okay? All right. So there are three key reasons why we want to have operating systems. There are three key benefits that we get when we introduce an operating system. The first one is protection and privacy. So you're going to have multiple processes here. These processes don't necessarily trust each other. They might be malicious, they might be buggy, and so you do not want these processes to interfere with each other. And so the first thing that we're going to do, or one of the most basic things that the operating system does, is protect processes from each other. Make it so that each process is isolated and can only access its own data, but not data from other processes. The second one is abstraction. And this is really, really important. Now, how many hard drives or how many peripherals can you buy for your computer? There's thousands of different devices that you can plug into your machine, right? And so it would be insane if you were writing programs that were directly interfacing with each possible device, right? Imagine if when you had to write a Python program, you had to say, well, if you have this hard drive, then write, I want to write some content, so write to this sector over here, write to this particular piece of the hard drive. I mean, nothing would work. Right? So instead, what the operating system does is it abstracts the details of the underlying hardware and it gives higher level interfaces. So for example, you do not write, when you write a program, you're not manipulating a hard drive directly or you're not issuing commands to the disk. In fact, you're opening files. Right? And so files are sort of the abstraction that we build on top of storage devices to essentially make processes able to manipulate data and have long-term storage, non-volatile storage, without concerning ourselves with the details of the hardware, right? Okay, the third big benefit of having an operating system is resource management. So this operating system is essentially in charge of controlling how all these different processes are going to use the different parts of the hardware. Who is going to get access to the CPU? Who is going to get access to what memory? Right? Who is going to get access to different I/O devices? Right? Who can open network connections and so on. Okay, any questions so far? So there are three key mechanisms that we use to get these three key benefits. And so this slide summarizes everything at a very high level, and then what we're going to do over the next 3 lectures is dive deeper into each of these mechanisms. The first one is, as I said, to protect different processes from each other. The OS kernel provides a private address space to each process. So each process is given some amount of memory, of physical memory, by the operating system, and then a process is not allowed to access memory that's outside of its own address space, right? So this is how it looks like, right? So you have memory, you have some physical memories over here, right? So different addresses are in different, addresses basically go down over here. And so you see that the OS kernel takes some of the memory of the machine, and then there's some blocks of memory that are dedicated to different processes. But if you're running on, for process 1, all process 1 sees is this amount of memory over here. Everything that's above or below is basically out of bounds. It's invisible to it, Okay? So essentially, yes?
So the processes, they are not written in assembly?
No, processes are written in, eventually they will be compiled down to assembly, or as we will see this in more detail in a couple of slides. But yes, they're not, they can be written in assembly, or they can be written in higher level languages. They can be written in assembly, yes.
And then how does the operator system knows, like, how much to allocate?
We will see virtual memory in detail in the next lecture, right? So for now, just at a high level, all you need to understand is that there is some amount of protection so that, a process can see some part of the physical memory, but not all of it. Okay, so this is essentially what we call virtualizing memory, and we will see this on the next lecture. Okay, the other thing that we need to do, the operating system kernel needs to take care of is essentially scheduling processes, right? Deciding how different processes share the CPU over time. So we have one processor, at least in the systems that we've built so far, there's one CPU, right? There's one processor. Now in the systems that you have today, there's multiple, but in general, you're gonna have many more processes than processors. So for example, whoever of you who has a laptop, can you tell me how many processes you have in your machine? Can you take a look and see just how many are running? Yes?
So I have 404 processes.
Right.
But only 2 of them are running and the rest are sleeping.
Right. So in general, you'll have hundreds of little processes that are taking care of different things in the machine, right? But a couple of them are running because probably you have 2 cores in your machine. Most of them are either waiting for some event to complete or sleeping because they have nothing to do. But in general, we're going to have this problem that when there are more processes that want to run than we have CPUs, and in our case, again, we have a single CPU, we're going to have to do something like this, where we're going to have to split the CPU over time and essentially give different time slices of the CPU to different processes, right? So, in this diagram, you see time going this way, and so in the beginning you have process 1 running, and then after a while, after a few tens of milliseconds, then the operating system steps in and decides to give the CPU to process 2, and after a while it decides to step in again and give the CPU to process 1. And this keeps going, and so what happens is that its processor believes that it's running on its own CPU. It's just a CPU that's kind of slow, right? It seems slower than if it was running alone. The final piece of the puzzle is that the operating system kernel lets processes invoke some other system services like files, like sockets, like all sorts of events via a mechanism that we call system calls. And this we will see 2 lectures from now. So there are multiple ways that you could implement operating systems. One way would be to start establishing calling conventions between applications and the operating system, and sort of make the each process very aware that there's an operating system behind it, below it. And so in general, we don't do this, right? And we want to keep a very high level abstraction. And the way operating systems achieve this is by implementing what we call a virtual machine and giving a different virtual machine to its process. And what I mean by this is that each process really does believe that it runs on its own machine, on its own physical hardware. But this machine doesn't actually exist in the physical world. It's just a mirage. It's just something that the operating system is providing underneath. And so in general, every time that we have a machine or something that looks like a machine that a process is running against, but that is not implemented in physical hardware, by contrast, it's not physical, we call it a virtual machine. Okay, so here's how it looks. You have the physical hardware at the bottom with all these devices, right? And then you have the operating system kernel, this specially privileged process that's running directly above the hardware. And then you have different processes. So for each process, for process 1 over here, right, you have this ABI that consists of a virtual processor, some virtual memory, and then different system calls, files, sockets, different events, and this is all provided by what we call the virtual machine, right? A virtual machine for this process. So the operating system kernel is emulating this virtual machine 1, but there are other processes running on the machine, and for each of those, the operating system is emulating a different virtual machine with its own ABI, right? Okay, any questions? So virtual machines are essentially a new layer of abstraction, right? We're basically saying we want to give this illusion that we have a machine, but we don't necessarily have to implement it in hardware. So far, we've seen machines that are directly implemented in hardware, right? But that's not how we're going to operate from now on. And so this is a staple of operating systems, but it's actually a very general concept. It's used all over the place, right? It's used in programming languages. It's used for virtualization technologies. And so you might have seen the term virtual machine used in multiple contexts. And basically the reason it's used in so many contexts is because it's always referring to the same thing, right? So we say that a virtual machine is an emulation of a computer system. So again, every time that you have some notion of a process, right, some sort of running program, that's not running against real hardware, but it's running against some sort of conceptual machine that is implemented by a process underneath, what you have is a virtual machine. What that process that's running underneath, that's implementing the machine, is implementing a virtual machine. And so in this case, the operating system kernel is implementing a virtual machine, right? Okay, so let's see this in a little bit more detail. So don't turn your handouts. So without looking at the handouts, can you tell me how many virtual machines did you use in Lab 4? 1, 2. Well, I mean, clearly we gave you a virtual machine, so at least that's 1, right? Okay, so let's go from top down. So first, you started writing some process in some program in assembly, right? And then you run it, right? So at that point, when you run it, that's a RISC-V process, right? That's running sort, bubble sort, quick sort, what have you, right? And so that process is interacting, and it's coded against the RISC-V ISA. But in fact, we were not giving you hardware that implements a RISC-V processor, right? What we gave you is we gave you a RISC-V emulator. That's a process, right? This was some Python program called sim.py. And this, in fact, is implementing a RISC-V virtual machine, right? This emulator makes it look to this process like it's running on a RISC-V processor, but in fact, it's doing everything in software. There's no hardware going on here, right? It's all a simulation. It's an emulation. Now, this is a Python program, right? So in the end, this sim.py is a text file. There's no x86 instructions. There's no assembly here. And so in fact, this is coded against the Python language. And what's underneath the Python language? Well, there's another program that's called the Python interpreter, right? In this case, this is CPython. This is a program that actually does have machine instructions, and it is implementing another virtual machine, right? The Python virtual machine, right? This is taking the sim.py file, interpreting its different statements, and then executing, right, the sim.py process under, it's translating those high-level statements into low-level operations, right? Okay, so that's 2 virtual machines so far. Okay, so this is a Linux process, so it's coded against the Linux ABI. Right, and beneath the Linux ABI lies the Linux operating system kernel, which of course is implementing a Linux virtual machine, a Linux x86 virtual machine. So at this point, what you have is an operating system, right, and a process that's itself a virtual machine, that's itself that's running another process that's itself a virtual machine for this other thing. Okay, so this process, this Linux operating system kernel is talking x86 ISA, right? It's running against an x86 processor, and it is sort of talking hardware directly, right? But that's not the end of the story. This is not actually running against hardware, right? Because what this is running against is VirtualBox, right? Which is yet another process that you downloaded for your own operating system, whatever that is. And that's implementing yet another virtual machine that's emulating hardware, right? It's making this Linux OS kernel here believe that it actually is writing to a disk, when in fact it's actually, what this is doing is translating these disk commands and saying, nah, actually I have the whole disk image here in some file, and I'm going to translate it back to file, read and write commands. And so this is coded against, there are multiple versions of VirtualBox for, one for whatever operating system you might be running. So maybe you're running Windows, Linux, macOS, FreeBSD, what have you. And so you're running this VirtualBox process on top of your operating system. And this operating system, again, is implementing yet another process virtual machine, which is talking x86 ISA, which, unless you did some other nested virtual machine, is talking with hardware, right? Okay, so how many virtual machines do we have? 5. So this is kind of mind-boggling, right? How many layers of translation from a RISC-V instruction until that actually runs on hardware? Okay, so 2 things. 2 important things. First, these are different types of virtual machines, right? So you can distinguish, first of all, at the lowest level, what we have is this RISC-V virtual machine and this x86 system virtual machine are emulating hardware, right? We call these system virtual machines or hardware virtual machines or full system virtual machines because they're making whatever's above them believe that they're running directly in hardware. Then you have these operating systems, right, which are implementing process virtual machines, right? They're giving this more abstracted interface to the processes that are running above the OS, right? And then finally you have this Python virtual machine, which is what we call a language level virtual machine. Right, so that tends to be more abstracted. It's further away from hardware. When you're writing a Python program, you don't necessarily. there's a notion of a process, right? But it's not very related to specific, the specific instructions that you're going to run in your processor. Okay, any questions? Yes.
Does VirtualBox always emulate x86, or does it use whatever the host machine is using?
So you can do multiple things depending on whatever virtualization software you are using. In general, they tend to be restricted to emulate the same underlying ISA, but there are virtualization packages that will emulate different ISAs like QAMU. So you can, if you're doing any iOS development, for example, what happens is what you're using is a virtual machine that emulates ARM on x86. Right, and so you'll frequently run into some of these. Okay, so finally, when we get to the physical world, there's as I said, there's the issue of which type or at what level of virtual machine we're talking about. Whether it's language level, process level, or system level. But there's also another factor here that's very important, which is performance. Right, so some of these virtual machines are introducing a significant performance slowdown, but some of them are actually not introducing a lot of slowdown. So, for example, the Python virtual machine, right? Whenever you run a Python program, it's no common knowledge that unless you're doing something, fairly special. Like using NumPy all the time or some library that's implemented very efficiently, you're typically incurring 1 to 2 orders of magnitude worth of slowdown versus if you just run something that's directly machine code, right? For example, if you took a C program and compiled it, that would be 10 to 100 times faster. And so the problem is that's very simple, right? And the reason is, well, we're implementing everything in software, right? So basically everything the process does, we need to somehow emulate. But when we're talking about operating systems, it's not acceptable for us to incur 1 to 2 orders of magnitude worth of overhead. And so because we want to support operating systems with minimal overhead, what we're going to do is add some hardware support to our machines so that we can essentially have most of the time, the program, at the higher level of abstraction, running directly on the underlying hardware resources. And then what we'll do is the operating system will step in whenever it's required, whenever the program tries to do something that it shouldn't, or the program requires some service from the operating system. Okay, so more specifically, there are 4 different things that we're going to see over the next 3 lectures, 4 different ISA extensions that we're going to introduce to support operating systems and to support these process-level virtual machines. The first one is that we're going to change our processors to have 2 different modes of execution, user and supervisor. So only the OS kernel is going to run in this special supervisor mode, and then all other processes are going to run in user mode. And the reason that we introduce these 2 different modes of execution is that we're going to give the supervisor mode some superpowers that the users are not going to have. So we call these privileged instructions and registers that only whatever process is running in supervisor mode has access to. So if you have, essentially there's going to be some hidden state that's not going to be available to most of the programs, but then the OS is going to have access to that state. Then the key question is, well, how do we transition between the user mode, or whatever process is running in user mode, to supervisor mode safely, right? How do we switch between these 2 modes? And this is accomplished with what we call exceptions or interrupts. And so that's the mechanism that we'll see today. And then the other key piece of hardware that we need to introduce is essentially what we call hardware support for virtual memory. And this is what will let us introduce this notion of having private address spaces with very low overheads. So we will see all these 3, the first 3 mechanisms today, and then next lecture we'll dive into virtual memory. But the key takeaway point, regardless of all these mechanisms, is that all these ISA extensions really only work if both hardware and software are very much in sync, right? You need the operating system to be very, very aware of what the contract is with hardware, right? And to know what the conventions are and what the interface is. And so we'll see these both today. We'll start diving into specific implementation details, and tomorrow in recitation. Okay, so the first mechanism that we're going to see are exceptions. So essentially an exception is an exceptional event, right? It's something that's not common just by definition. It's some event that needs to be processed by the operating system kernel, and this is either unexpected or rare. And so basically you have some process over here, right? It's running some sequence of instructions, instruction I-1, instruction I sub I plus 1, and then on instruction I sub I, something happens, something unexpected happens. This exception triggers. And so what we're going to do is redirect the processor to execute instructions from this handler code, this operating system code that's in the OS kernel, and we call this code the exception handler. So this handler is going to essentially run through a sequence of instructions, figure out what to do, and then return control back to the process. Now, there are many different reasons why exceptions could happen, and generally we classify them between, we distinguish between what we call asynchronous events or synchronous events. So synchronous events are essentially what we call exceptions, and they're generated by the program itself. They're generated by the process. So, for example, the PC goes into an illegal instruction, right, or an unsupported instruction. And so now we don't know what to do, right? So that merits a call into the operating system to say, hey, something went wrong, figure it out. But there's many other reasons. For example, you might have a process that issues an illegal memory access. It issues an access to memory that it's not supposed to be accessed, or it is a memory access that's unaligned, right? Your address, you're trying to access a word, but it's not aligned to a word boundary, and so that will again trigger a call to the OS. There are also arithmetic instructions, right? So if you have a divider, you will get divide by 0 exceptions, right? Because I don't know what the results should be, right? So that's up to the operating system to decide. And also, sometimes the process itself wants to invoke the operating system with this system call mechanism that I mentioned before. And so we will see this in detail in a couple of lectures, but just be aware that the basic mechanism that's used there is also exceptions. On the other hand, we also have what we call interrupts. And interrupts, by contrast with exceptions, are asynchronous events. They're generated by other devices other than the program. So for example, you have a timer that's periodically interrupting the processor so that the OS can step in and do something, right? And so whenever this timer expires, it raises some interrupt line, and the CPU takes an interrupt and automatically goes into the OS so that that interrupt can be serviced. But also, if you have a keyboard, every time you press a key, right, there's an interrupt that's being raised in the CPU so that the OS can process it. When you have some I/O operation, let's say there's a write going on, and the hard drive, the disk, figures out that it's done. Give me something else if you have it. Again, that's going to raise an interrupt, and then the operating system needs to step in and figure out what to do. Okay, so in general, you'll see the terms exception and interrupt being used more or less interchangeably. In this course, we're going to use exception as the general term, and so we will use synchronous exception when we're talking specifically about these synchronous events. This is also in line with the RISC-V nomenclature, which uses exceptions to refer to everything. Okay, any question so far? All right, so as I said, when an exception happens, basically there's a very specific recipe that we're going to follow. The first one is that we're going to stop whatever, we're going to stop execution at the instruction where the exception happens. And we need to implement something that's called precise exceptions. So whenever there's an exception, we need to have we need to complete all the instructions that precede the instruction that caused the exception, and not have any, the instructions that follow the instruction that had the exception should not have any effect. So this is intuitive, right? I mean, if you have an exception at one particular instruction, everything above it or every earlier instruction should have been completed. Every instruction that comes after should not. But if you start thinking about, well, what's that going to do to pipelining, right? Where now we're overlapping multiple instructions, and there are side effects that happen at different cycles. So you'll see that in a couple of lectures we'll see exactly what hardware support this requires, and there are some nuances in how can you implement exceptions efficiently. But forgetting for a second about implementation details, conceptually what the processor is going to do is stop the program right at that instruction. Then it's going to save the PC of the instruction that where the exception happened, and the reason why that happened, is that an interrupt, is that an illegal operation, something else, in some privileged registers that only the OS has access to. And then it's going to toggle the supervisor bit, so there's going to be a bit that decides whether we are in supervisor mode or user mode. So it's going to enable supervisor mode, it's going to disable interrupt so that no other, so that the OS doesn't get interrupted when it's trying to handle this event. And then it transfers control to a pre-specified PC, a pre-specified address. So then the exception handler in the OS kernel runs, processes the exception, figures out what to do, and there are two possible options. One option is, that we could process this exception, or this is an interrupt and it doesn't actually have anything to do with the process. And in that case, what we're going to do is just return control to the process that was running at the same instruction. And so what's nice about this is that this is completely transparent to the process, right? The user process just saw a little blip in time, but then execution resumes at the same point where it was interrupted, and so there's no functionally there's no difference from if the process was running continuously. The other option is that this exception is actually due to something that the process did that it shouldn't have done. So for example, there was a bug in the program and you started trying to access memory that you shouldn't have accessed, or executing data as code and running to some garbage instructions. And so in that case, the operating system basically aborts the process, right? It just stops it, and that ensures that nothing bad happens. Okay, any questions? So, yes.
So since it's disabling interrupts when it handles the exception, what happens if the kernel throws an exception as well?
Bad things. So sometimes the kernel itself is stratified. So sometimes what will happen is that the kernel will have some special bit of code that's super carefully coded to not cause exceptions, and that will immediately re-enable exceptions. But there's some very specific interval where you don't want to get re-interrupted while you're trying to handle an interrupt. So, but yeah, that's a great question. And in fact, if you look at specific operating systems, you'll see that they'll talk about the top half and the bottom half. Top half is whatever handles interrupts, and that cannot be interrupted. And then there's the bottom half, which can be interrupted. Okay. So, let's see what can you do with exceptions and interrupts. And specifically, we're going to look at two different applications, or two different features that we can implement with this mechanism, which essentially do what we want with respect to the processor. They virtualize the processor. They give us a virtual CPU. The first application, the first case study, is essentially this scheduling feature that I mentioned before, right? So as I said, one of the key features of the OS kernel is that when you have more processes than CPUs, it needs to split or slice the CPU across processes. And so each process is given some fraction of the time in the CPU, and it cannot take more time than it is given. And the enabling technology for this is just a timer. It's what we call timer interrupts. So basically, there is some hardware device that's just keeping track of time. And then the kernel has some access to it, maybe through one of these privileged registers, and it's setting some timer. It's basically saying, interrupt me in 10 milliseconds or 20 milliseconds. And then 20 milliseconds from now, that device will raise an interrupt, and that will jump, that will make the processor jump back into the kernel. So let's see how this works in more detail. So here you can see the time in milliseconds, right? And we have the process that's running in the CPU. So let's assume that in the beginning we have the kernel that's running in the CPU, and now the kernel wants to give control to some processes, right? It wants to schedule some process in the CPU. So what it does before just giving the CPU to that process, let's say it wants to schedule process 1, is before it does that, it sets a timer. It says, in 20 milliseconds, please interrupt me. And then it loads the state of process 1 and gives control to process 1. So from, time equals 10 milliseconds to 30 milliseconds, process 1 is happily running on the CPU. But then at t equals 30 milliseconds, the timer fires. And when you get that interrupt, that automatically switches the CPU into the exception handler. Right, so you see that the kernel is running for this small time slice, right? You see this small time slice of orange here, and in this case, basically, the kernel figures out that this is a timer interrupt. So the time that this process has expired, and so now we need to schedule something else. And so in this particular case, let's say that there's a process 2 that also wants to run, and so we. The OS kernel decides to schedule process 2, sets the timer to fire in, let's say, 30 milliseconds, maybe 30 instead of 20 because process 2 has higher priority, so it deserves more CPU time, and then the process repeats, right? So at 60 milliseconds, the kernel is invoked again, decides to switch to process 1, and so on, right? And so with timer interrupts, as you can see here, what we can do is we can safely time slice, time multiplex the CPU among multiple processes, even though these processes have no idea that they're actually just running on a slice of the CPU at a time. right? Yes?
This timer, is it something like hardware?
Yes. This is a hardware device. So you'll have some quartz crystal that's keeping track of how many microseconds, milliseconds have
And only
passed.
the operational system can write to it.
Right. So the key thing is that only the operating system has access through this privileged mode to this timer, right? Otherwise, the process one could say, no, I actually want to run for longer. Let's set the timer to 50 milliseconds, right? To infinity milliseconds, and now the system is mine, right? So the key point here is that you don't allow processes to access this hardware, right? That hardware is only accessible by the operating system. Okay, any other questions? Yes?
What does the operating system use to gauge how long it could give everything?
That's a great question. So there's a million different scheduling algorithms. In recitation tomorrow, you'll see something very simple that basically is what we call round-robin scheduling. And then, how long should it have? Well, that depends on your implementation. You want to, because you have caches, you want to essentially let each process run for enough time that you're not just thrashing the caches all over the place, right? So if since these processes are not going to share anything, you at least want to keep the caches warm relatively. And so that tends to set a limit of a few milliseconds at least. Okay, and then on the other side, if you schedule a process for 4 seconds, then you're not going to have access to that process, to that CPU for 4 seconds. And so if you're doing anything interactive, you also want to set that interval to be small. So it's an interesting trade-off. Okay, what else can we do? Well, so the other thing that we can do with exceptions is emulate instructions that our hardware doesn't actually support. And so this we can do by doing, taking an illegal instruction exception and doing something interesting with it. So let's be specific. So far we've implemented, these RISC-V processors, and we've implemented the simplest subset, the 32-bit ISA variant. So that's RV32I. And there are multiple extensions that implement more instructions, and one of those that's very commonly implemented is what we call the M extension, and M stands for multiply, right? So the M extension defines this multiply instruction over here. That is essentially taking x2, the contents of x2, x3, and storing, multiplying them and storing the result on register x1. But of course, if we haven't implemented M, then that's implemented. That's the processor is detecting that as an illegal instruction, right? And so if we try to run code from an RV32IM machine, that is a machine with that multiply extension, on this basic machine, more basic machine like the ones we've built without a multiplier, what happens? So we get an illegal instruction exception, and then in that case, one simple thing that we could do is the OS will step in, and it can say, well, you tried to run something that I don't actually understand, or that's not in this ISA, so it could abort the process, but it can also see, this is a multiply instruction, and the hardware doesn't have multiply instructions, but I know how to do multiply, so we're going to emulate the instruction in software. Let's see how this happens. So suppose that you have this code over here in process 1, right? So there's this add instruction, and then there's this small instruction, and so process 1 is running over here, and then at this particular point, it steps into this small instruction, and that causes an illegal instruction exception. And then that causes the kernel to be called, and so the kernel is going to take a look, it's going to run the illegal instruction exception handler, and is going to see that this sequence of 32 bits that the processor, right, our hardware processor doesn't know how to interpret is actually a multiply instruction. So it's going to emulate it in software. Now, the OS doesn't have a multiplier either, but it can do multiplication by repeated addition with, a normal function call. And then, when it's done, it basically needs to return control to the process at the instruction following the multiply, right? And so the result here is that the program believes that it's actually running in a processor that does have hardware multiplier, right? It believes that it is running in this more sophisticated ISA, even though in hardware we don't actually have a multiplier, right? In a sense, we've virtualized the processor. We're making the program believe that it has hardware that it doesn't, right? Okay, any problem with this approach?
Overhead?
Yes, it's kind of slow. Yeah.
Didn't it say earlier that we return to the same instruction which we
Right, but this is an exception to that rule, right? Because if you're emulating the instruction that caused an exception, you need to return to the next instruction. Otherwise, you'll constantly run into the exception, right? Okay. So yeah, the problem is that this is still much slower than a hardware multiply. Yes.
Don't we also run into the issue where now our code isn't like agnostic of what it's running on, because like if we want to multiply numbers, we don't know if our OS will be capable of doing this exception.
Well, so that depends on what the contract with the OS is, right? If the OS guarantees that it's going to emulate those instructions, then it should. Otherwise, it should not, right? So that is specific to the OS, but it is, in a sense, the OS can choose whether to hide it or whether to not. Okay, so in the remainder of the lecture, we're going to start going into details into how exceptions are actually implemented in RISC-V. This is actually something that we're going to discuss in much more detail in tomorrow's recitation. But let's start, taking a look at what RISC-V does, so that we can get jump started into the recitation materials. Okay, so basically, as I said before, in general, an ISA has this supervisor mode, this user mode, and then supervisor mode has access to privileged state and privileged instructions. And in RISC-V, this privileged state is in the form of some privileged registers that are called control and status registers, or CSRs for short. So some of these are some famous CSRs, although there are many. Are essentially what we call MEPC. So all of these begin by M, and that stands for, this is machine level. And so this is the EPC, the exception PC. This is the PC of the instruction where the exception triggered. mcause, which is the cause of the exception. mtvec is the address of the exception handler, right? So this is something that the OS sets so that when an exception happens, basically the processor jumps to the address that's stored in that register. And then mstatus basically has a bunch of status bits telling you things like what privilege mode are you on? Are you in user mode, in supervisor mode? Are interrupts enabled or not? And so on. And then there are instructions, privileged instructions, CSR-R and CSR-W to read and write these CSRs. And then we'll see another instruction that's called mret that needs to do something fairly special, right? It needs to return from the exception handler to the process, and that is a fairly delicate dance of atomically updating different pieces of state. And of course, because these are privileged, trying to execute these instructions from user mode causes an exception. So if you have a normal user process that's trying to run a CSR-R, it will immediately go into the operating system, which will figure out what to do, probably abort the process. Right? Okay, so the typical way that we code these exception handlers, or that operating systems code these exception handlers, is there's what we call the common handler, which is in this picture shown here in orange. That's typically written in assembly because it needs to do a very delicate dance on how to switch contexts between the user level process and the exception and the OS kernel. And then we have a lot of other exception handlers, and those we write in higher level C code. And so then every exception goes directly to this common handler, and the common handler does 5 things. The first thing it does is it saves all the registers into some location in memory, right? And then it passes all the state, right, the pointer, or the address of this where these registers are stored at, to the particular exception handler that we're interested in running. Finally, we this exception handler returns, and it tells the common handler what process should run next. So normally we'll run the same process. If this is a timer interrupt, we might switch to a different process. If the process did something bad and the exception handler aborted it, then it will also switch to a different process. And then the common handler does sort of the reverse thing. It reloads the registers from memory into the actual registers, and then it returns. It calls mret, which does this fairly difficult dance of setting different pieces of state at the same time. So it takes this MEPC and sets the PC to it. It also disables supervisor mode and re-enables interrupts all at the same time, so then we jump back into process code. Okay, so the code that you'll see tomorrow is how to both implement the common exception handler and also how to implement the dispatcher into different exception handlers. This is what you'll see in recitation tomorrow. So in summary, again, key goals of operating systems: protection, abstraction, and resource management. Today we've seen how to do this, we require some hardware support to do this efficiently. We've seen how you can do lots of different things with user mode and supervisor mode, and with exceptions. And in next lecture, we'll start our discussion of virtual memory. Thank you.